Refraction of Light by Shannon and Ali. So what makes light refract? In order for light to refract, there first obviously needs to be light, and the light needs to travel from one media to another. And the media could really be anything at this point, it doesn't really matter. And if this is right here is the media boundary, and say this is the incident ray.
You're all set, you just hang it out.
And that's the ray that hasn't been refracted at all yet. After it passes through the second media, it'll refract and become the refracted ray. The index of refraction is the ratio of the speed of light in air, which is expressed as the letter c, to the speed of light in the medium through which it passes, which is expressed in the letter v, and the index of refraction is expressed as the letter n. The equation for this is n equals c over v. Now, if you're trying to find the speed of light in a medium through which it passes, in this case we're doing lucite, it would be n, which is 1.51 in lucite, equals c, the speed of light, which is 3 times 10 to the 8th meters per second, over v, which is what we're trying to figure out. Now, simplified, we could write this out as 1.51 v equals 3 times 10 to the 8th meters per second. And then we could divide each side by 1.51. And then we would get v equals 1.9 times 10 to the 8th meters per second. And that is the speed of light in lucite. Refraction away from the normal line. A ray of light refracts away from the normal line when the light travels from a medium with a higher index of refraction to a medium with a lower index of refraction. So really, in order to determine which way it's going to refract, you need to compare the indexes. So in this case, it's water to air, which means if water has a slightly higher index of refraction than air, the incident ray, which looks like this, is going to pass through the media boundary and the normal line, which is always perpendicular to the media boundary, and refract slightly this way to the right. And we measured it by using the little angle indicators up here and found that it refracted, the incident ray was 30 degrees away from the normal line, but the refracted way was 42 degrees away from the normal line. And in this case, it's the same thing, only it's lucite to air, and lucite has a higher index of refraction, so the incident ray went like this, and then refracted 18 degrees away from what would have been just the straight unrefracted line, or 38 degrees away from the normal line. Refraction towards the normal line. A ray of light refracts towards the normal line when the light travels from a medium with a lower index of refraction to a medium with a higher index of refraction. So when the normal line goes down like this and the media boundary is from air to water, air has a slightly lower index of refraction than water, so the incident ray went up like this and then refracted into this teal line here, which is only 22 degrees away from the incident ray as opposed to 31 degrees away of the incident ray. And the normal line here is perpendicular to the media boundary, which is air, and then to lucite, and again, air has a lower index of refraction than lucite. So the incident ray refracted up like this, and would have just gone straight through, but it is now, or the refracted ray went towards the normal line 20 degrees rather than 29, which is how it was before. So what determines the amount of refraction in a light ray? The amount of refraction is determined by a difference in the two index of refraction. So say, here's your media boundary and here's your normal line. And say this media has an index of refraction of 1 and this one has 1.2. When the light ray refracts, it'll go through the normal line, and then because the difference is from a higher medium to a lower medium, it'll refract away from the normal line, but only slightly, because the index of refraction difference is so low. Now, if there was a much higher difference between the two index of refraction, say it's one media has an index of refraction of 1 and the other has an index of refraction of 1.8, the amount of refraction is going to be much more dramatic, so it'll refract away from the normal line maybe at an angle that looks more like this. So the magic penny activity. The penny can be seen at first in the video like this because of the light rays reflecting off of the penny and into our eyes, but once we move away, we can't see it anymore. But when we add water, you can see here that the image of the penny starts to rise up in the pan, even though we haven't moved, and obviously neither has the penny. So this is the magic penny explained. Now what really causes it is not just one type of refraction, but two. So I'll draw in a normal line really quick, because we need something that's perpendicular to the media boundary. And here is the incidental ray that just comes from the light in the room, and when it passes through the normal line, it diffracts just a little and hits the penny, which is the little brown dot. And then there's another type of refraction that takes place, and I'll draw another normal line that happens when the light ray reflects from the penny up here and then refracts again, except away from the normal line this time because it's passing from water to air. So then the refraction looks like that. And here is our incidental angle, and our angle of refraction won't fit there, but here's where it is. And this is our incidental angle here, and our angle of refraction here. And that's what ultimately causes the penny's image to appear over here, like the little ghost penny. The end, and thanks for watching.